Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is Chapter 7, Section 2, so 7.2, which is regarding volume, specifically the disk washer method. Technically, there are two different methods, the disk and the washer method. All right. So we'll first discuss the disk method, and then we'll see why or we'll talk about the washer method and see why it's very similar. So first, let's recall something. Recall the volume of a cylinder. All right. Now the volume of a cylinder. Well, let's think about a cylinder. Well, that's given by the area of the base. So here the volume is the area of the base, which is a circle, so pi r squared, and then that times the height. So that's given that this is the height, and that is the radius, right? So with the volume of a cylinder. Now let's consider what a disk is. A disk is just a very flat cylinder. All right, perhaps I'll draw that bigger. So it is a very flat cylinder. All right, and here this is the height, and similarly this is the radius, right? So we're going to be using this idea of the volume of a disk to figure out some volumes here. Now let's think about how to get something like that out of a graph. So first, let's think about this. If I had this little rectangle here, right, in here, this, if I rotate it this way, right, well, if I rotate that this way around the x-axis there infinitely many times, well, what do I really get? Well, let's do this. I end up with the following. So this is going to go to that. We're going to end up with a disk being drawn there as we rotate this, right? Ooh, that's a horrible drawing. Does that help? Yeah, I guess it's a little bit better without the extra lines. The idea here again is that this is a disk now. All right. We started with this, we rotated it to end up with this disk. All right. In this disk, notice that this is the radius. So this is our radius. This piece. That's our radius. And this right here is the width. So this is the width. Now, that's just for one rectangle like that, right? But we can expand this idea to say, well, what if we had a curve on something like this, right? So let's say that I had something that went like this, all right? And in there, I'm just going to take a representative rectangle here. Let's see this one right here, right? I'm going to take that representative rectangle and we're going to rotate this about the x-axis, right? And what is that going to give us? Well, let's see the visual over here. So over here, when that gets rotated, well, we get something like this. Where this is being rotated, right? So this goes all the way down here and over here. And this piece right here creates this disk right here. Right? And the idea here is that, well, everything here, this right here, this disk in the middle, this disk, that's just a representative disk out of all the possible disks here, right? So in here, I'm still gonna call this my radius, right? That's still my radius. But now this width, I'm gonna call it delta x, and the radius is being based off of this function. So it's gonna be r of x, all right? So over here, we still have the same exact idea of this piece right here being delta x, and this right here being r of x, this distance. All right, now let's think about this a little bit further. Recall that this is just one representative disk, so there's a whole bunch of others, right? Like that one, and then I could do this last one over here, all the way around there. The idea remains that there's a lot of these disks. Now, to figure out the entire volume of this, well, what we're going to do is we're going to add up each of these disks. So our volume is going to be the sum of a whole bunch of these disks. Now, each of these disks has its own volume, and we already know what the formula for the volume of a disk is, pi r squared times height. So we're adding pi r squared times height over and over again, right, for each of those disks. So if we start adding and adding and adding more and more of these disks, we end up with, well, the true volume being the limit as n goes to infinity of the summation from n equals 1, right, the first disk to the infinitely many disks of, I'm going to put this pi out here because it's not being affected by the n here, but r here, radius, I'm going to call it, I'm going to say we have r of x sub I squared, right? X sub I just being our representative x somewhere in the interval, times our height, right? Now our height, what did we say it was? Well, I called it width over here. I really should be calling these widths. But it's the same, the idea stands, right? That this height over here, sorry, this height is really the width that's right there. So instead of height now, we're multiplying by the width, which is delta x. So this gives me now the integral, right, because I'm taking the limit here. This gives me now pi times the integral from a to b, and we'll talk about what a and b are in a second, of our radius function squared dx. All right. Now in here, what's a and what's b? Well, a and b would be the region that we're working in from a to b. All right. So in here, here's a, here's b. All right. So just the region that we're rotating in here. This is the entire region being rotated, right? So there we go. That's our formula, all right? And that's going to be about a horizontal axis. So let me formalize that. So in here, the disk method. The disk method is, so given, well, let's write it this way. To find the volume of a solid of revolution with the disk method, use the following. So we're going to say if we're rotating about a horizontal axis, right, which is what this explanation was, we were rotating about a horizontal axis. So use the following. So if we're doing a horizontal axis, so a horizontal axis, we're going to say that the volume is equal to pi integral from a to b of our radius with respect to x squared dx. All right, and this is assuming that our region is bounded between a and b. So that's for a horizontal axis. For a vertical axis, well, the idea remains the same. We're just doing things vertically, so it's going to be things in terms of y now. So it's going to be the integral from c to d of r of y squared dy, where y is between a and not a and b, c and d, right? My bounds, c and d, right? So that's the formula. And again, for the vertical axis, for that vertical rotation, the idea stays the same as what we did to come up with this, but everything's being rotated this way now instead, right? But the idea stays the same. Okay, so now let's uh, let's do a couple of examples. So example A, find the volume of the solid of revolution bounded by, so let's see, let's say that we have f of x is equal to the square root of sine of x. We're going to say also by y equals 0, right? And we're going to say in the first quadrant. In first quadrant, all right? So let's see what we get here, all right? So let me show you the graph of this. Here, this is the visual. We've got the square root of sine of x looks like this, right? We're here, this is pi, this is 0, and oh, I should say about what axis we're rotating. So rotated about the x-axis. So our axis of rotation is just the x-axis. Okay. So this is a region, right? This is the region that we're working in. Now in here, what I want to think about here is, well, if we're rotating this way about the x-axis, well, what's our radius? Our radius from our axis of rotation is just that distance, right? And that distance is given by our function. So what we're going to get now is that the volume is, well, pi times integral from, so we're doing a horizontal rotation, so it should be from a to b of our radius with respect to x squared dx. All right, so in here, what did that really mean? Pi integral from a to b, so 0 to pi of our function r of x, and that function is just radical sine of x, and that squared dx. So what does that do for us? Is squaring the square root here. Well, I have pi integral from 0 to pi of sine of x dx, which means pi times the integral of sine is negative cosine, evaluate from 0 to pi. So plug in pi, so I have pi times negative cosine of pi minus pi times negative cosine of 0, right? And then cosine of pi is negative 1. Negative 1 times negative 1 is positive 1. So positive 1 times pi is just pi. So I have pi minus over here. Cosine of 0 is just 1, right? And then, so times is negative, so I have negative 1. So I have minus negative pi. So this gives me 2 pi. And again, what I did here was I said that this cosine of pi is negative 1, and this cosine of 0 is just 1. But negative 1 times a negative gives us a positive, positive times pi, positive pi. 1 times negative 1 is negative 1 times pi, negative pi. Okay, so that's our volume, all right? And as far as what that looked like, or what that would look like after rotation, well, let's see how great my drawing skills are here. But this should be a good idea of what it is. So it ends up looking like that, right? Um, where what we're doing here is we're making these disks. Well, let me do it this way. Those are all the disks that we're making, right? All throughout here. By the way, I would recommend you do get into the practice of drawing a representative rectangle. All right. I should have done that at the beginning of this one, but that's okay. I'll do it at the beginning of the next one. But yeah, that's essentially what we get there. And again, this is all just filled in, right? And it's a three-dimensional object there. All right, cool. So next one, let's see what else we can do. Example B. So let's say that I have y equals radical x. So this is the region. I'm describing the region, right? Y equals radical x. Y equals 0. We're gonna say between. Well, let's do it this way. Let's write this as the lines x equals 0 and x equals 4, right? And we're gonna rotate about x-axis. Okay, so let's see what we can do here. Well, let's get an idea of what this region looks like. So in here, so we've got radical x. Well, radical x looks like this, right? The line y equals 0. The line y equals 0, that's just the x-axis. The line x equals 0. The line x equals 0. And then the line x equals 4. That is here. I'm actually gonna remove that x equals 0 from these instructions because that's not really helpful for this region. So let's do it this way. So this is the region that we're rotating, and we're rotating it around about the x-axis. So in here, let's start by drawing a representative rectangle. So this is my representative rectangle, right? And since I'm rotating about the x-axis, my radius here is just this distance, right? That distance right there. So what happens when I rotate this? Let's see. Let's get an idea as to what this is going to become. So we're going to get a shape that looks something like this, right? Let's make all of this. I'm going to get rid of that. And, ooh, now what I meant to do. There you go. And when we rotate this, well, what do we end up with? Well, something like this, right? Right, with a whole bunch of disks there. So what is that going to do for us? Let's see in here. Well, let's say our volume is going to be, well, we're still rotating about a horizontal axis, so we know that it's pi times the integral from a to b of r of x squared dx. Okay, what does that mean? Here we're going from 0 to 4, right? So that's our x bounds. So we have pi integral from 0 to 4 of our function r of x squared. Well, what is this distance right here? That's our radius. What is that distance? Radical x. So I get radical x squared dx. So in here, really what I'm looking for is pi times the integral from 0 to 4 of just x dx, which gives me x squared over 2, evaluated from 0 to 4, which gives me, well, let's plug in 4, so I have 4 squared pi over 2 minus plug in 0, 0 squared pi over 2. 4 squared, 16. 16 over 2 is 8. So here I end up with 8 pi. So now let's do something that's similar to this one. All right. But now, let's change it up. So I'm going to be working with a similar region here, but now I'm going to say y equals radical x. We're going to do x equals 0. We're still going to do from, well, no, we're not going to do, well, yeah, I'll blame it. We'll call it that, from 0 to 4, all right, in that region. And yeah, we'll leave it as that. That's the region that we're going to do. Oh, let's change the axis about the y-axis. So let's see what we get here. In here, well, let's look at that region. Well, luckily I already drew that region, but we're gonna, or something like that. But let's redraw this, because this is no longer important. We've got now the line y equals 0. Well, that's the x equals 0. That's just the y-axis, but we're going up until x equals 4. So we're going up until that point. And we're rotating it this way, right? We're rotating about the y-axis. So really the region that we're looking at is, well, this continues. We're looking at this region right here, all right? Now, how did I know that? Why is it not this region over there? Well, the reason it's not this over here is because of that line. That x equals 0 tells me that that needs to be part of the boundary. All right, so I have the line x equals 0, have the curve y equals square root of x, and the fact that this is going from 0 to 4 tells me that this value right here would be my maximum on that region. All right, so in that region, well, we're rotating about the y-axis, so this right here is going to be my representative rectangle, right? I'm going to call that the representative rectangle, so my radius here is just this distance. That's my radius. So in here, let's see what we get. Well, our volume now is going to be pi times the integral. Notice that we're doing things about a vertical axis now. So we need to do things from C to D of our radius with respect to y squared dy, all right? So we need our radius function to be in terms of y. Well, that poses a problem here, because our function was in respect to x. But we can redraw that. We can figure out what that is, right? And this is what we do. We say, well, if y equals the square root of x, that tells me that x is equal to y squared. And look at that. Now I've got a function of y, right? So everything needs to be in terms of y. Before we actually do this integral, though, let's go ahead and get a visual as to what we're looking for. So I'm going to put this over here, more centered. And let me erase some things here. All right. So what we end up with here is something like this. Let's say that's -4. All right, so something like that, where this is, well, let me draw that better. There we go. So it kind of looks like a tornado, right? Or like a funnel, I guess. Either way, well, that's what that's gonna be. All right, so now let's figure out this this setup. So I'm gonna go ahead and copy this down here so that we can see what we're doing. All right, now what we're gonna say now, well, if x is our function, y squared, right? That's how we're gonna write that in there. Well, that's our function there. But now our bounds, what are they going to? Well, they're going from this value down here is 0, but what is this height at? Well, this height is when x equals 4, right? And it's hitting the function. Perhaps it's a little bit clearer here. This height here what is this point? Let's figure out what that point is. Well, the x value is 4, but the y value, I can plug it into this function, into this curve, which was square root of x, right? And that gives me the point 2. So that tells me that this height is at 2. So now, that tells me the upper bound. So what we can say now is that our volume is now going to be pi the integral from 0 to 2, right? Our upper bound there, right? That was our line 2 of our radius function in respect to y. And we said that that was just simply y squared, and that squared dy. All right? And again, that's because we're trying to, there's right here in blue, that's our radius. So that distance is just hitting that function there as y squared. All right, so in here, what does that give us? We have pi integral from 0 to 2 of y to the 4th dy, which gives us pi times y to the 5th over 5 evaluated from 0 to 2, which at that point, well, what do we get? We end up with 2 to the 5th pi over 5 minus 0 to the 5th pi over 5. This thing here goes away, right? That's just 0. And 2 to the 5th is 32, so I end up with 32 pi over 5. All right, so now let's see what we did here in these couple of examples. In example A, we rotated about the x-axis, right? In example B, we then rotated about the x-axis again. And here we rotated about the y-axis, right? But the idea with every single one of those is the same. But we were just rotating about the given axes, x and y axis. There's no reason why we need to rotate, like why our axis of rotation has to be the x-axis or the y-axis. So for example, let's do this. So we're gonna say, let me give you the region. So the region bounded by f of x is equal to 2 minus x squared. G of x is equal to 1. And we're rotating about, so it's region bounded by those two, rotated about the line y equals 1. Okay, so let's see what we get here. So let's figure out what this region looks like, and then we'll see what we're actually looking for. 2 minus x squared. 2 minus x squared looks like this. It is a parabola where that value there is 2, right? And then g of x equals 1. Well, that's just that line there. This is, so here we have, this is f of x, this is g of x. And we're rotating about the line y equals 1. So we're rotating about this. And this is the region that we're rotating, right? Because it's the region bounded by f of x and g of x, that region. All right, well, let's see what we do here. As far as concept goes, it's the same exact concept than we've already spoken about, right? In here, this is going to be my representative rectangle, all right? This little rectangle here. Now notice here that this is my radius now. That distance is the radius. So, and it's based off of this line, right? Because again, that's where we're rotating. So let's see what we get here. We're rotating about a horizontal axis, so my volume is going to be pi integral from a to b of our radius function squared dx. But what's our radius now? Let's see. In here, my radius is, well, this distance, this distance here. Well, what is that distance? That's going to be 2 minus x squared minus 1. How did I get that, right? Well, I did this, the top, minus the bottom, right? 2x squared, 2 minus x squared minus 1, which is really just, well, 2 minus 1 is 1, so it's 1 minus x squared. So that's my radius function, all right? So in here, if when we're rotating about a different axis that is not the x or y axis, we have to account for that when we're figuring out our radius functions. Which is why in here, well, now we're going to say that in this case, we're going to go, ooh, let's figure out what A and B are, because that is this point and this point. How do we figure those out? Well, we need to set these two functions equal to each other. So we're going to say 2 minus x squared is equal to 1. So I get 1 minus x squared is equal to 0. So I get really that x is equal to plus or minus 1, right? So in there we can say x is equal to negative 1 and x is equal to 1. So in here now, instead of saying a and b, we're going to say from negative 1 to 1. All right, and notice I used x values, right? Because we're rotating about a horizontal axis. So rotating about a horizontal axis, we want x values for this method. So now, what do we get here? We get pi times the integral from negative 1 to 1 of our radius function, which we said was 1 minus x squared dx. All right, and at that point, well, let's integrate that. So what do I get? I have pi integral from negative 1 to 1. Expanding this, right? If I expand this, I end up with 1 minus 2x squared plus x to the fourth dx. And integrating, well, I have pi times the integral of 1 is x minus the integral of 2x squared is 2x cubed over 3 plus the integral of x to the fourth is x to the fifth over 5, evaluated from negative 1 to 1. All right. Now, in here, I'm going to skip the steps of actually plugging all this in. I'm going to leave that up to you. The point is you plug in 1, plug in negative 1, and if you do it correctly, you should get 16 pi over 15. So that was finding the volume of a region, of a rotated region about a horizontal axis that wasn't the x-axis. So let's do something similar, but along the y-axis, right? So here we go. So example E. And here I've got, well, let's say that I've had this function. X is equal to negative y squared plus 4y. And we're going to say rotated. Oh, well, I should also give the other line. So the other line we're going to say also x equals negative 5. So it's bounded by those two. Rotated about x equals negative 5. All right. So let's see the visual for this. And in here, what do we have? We have something like this. This right here is a sideways facing parabola. That's a function of y. So it looks something like this. All right. Where this point right here is 4 and this point right here is 0. And I have this line x equals negative 5. Let's say that this is it. That's the line x equals negative 5, right? And in here, what we're doing is we're rotating this entire region here, around that axis, -5. Well, let's see, what do we do? Well, the first thing I'm going to do here is figure out what the representative rectangle looks like. And the representative rectangle would be this, right? So that tells me that this entire distance is my radius. Now, because we're rotating around a vertical axis, right, we're going to be using everything in terms of y. Now, what does this look like rotated? Well, let's do this. Let's say I'm going to copy and paste that. It looks something like this. Let's see how good I am at drawing this again. Ooh, that was awful. Yeah, something like that. Um, and in there, well, that's essentially what we've got, right? Um, where this right here is our y-axis, but this over here is our axis of rotation, right? All right. So now let's see, what are we gonna do here? Our formula when we rotate about a vertical axis is pi integral from c to d of r of y squared dy. Now, to do this, well, what do we need? We need c and d, and we need our radius function. Let's see what those would be. C and d, well, that's supposed to be this height up here, and this height up here. Well, what we can do is we can set this function of y, equal to this line to see what values those would be, right? To figure out where they intersect. So that function again was negative y squared plus 4y, and we're setting it equal to -5 to figure out where they intersect. So moving the -5 to the other side, so I get negative y squared plus 4y plus 5 equals 0. I don't like this negative there, so let's just change the sign of everything there by dividing by -1. Factor in this, two numbers that multiply to -5, but add up to -4. Well, that's going to be -5 and +1. So that gives me that y equals -1 and y equals 5. Okay, so -1 and 5. So now we know what the bounds are, the entire region there. Okay, so we have now that, but so now we have C and D, but we also need our radius function, right? Our radius function. So that's this entire distance. And in general, the distance between here is going to be the big value minus the small value. So big value minus small value. So that's the distance between two things. So the big value is the function -y squared plus 4y, that function of y, and the small value is -5. So what I'm saying there is that r of y is going to be -y squared plus 4y minus -5, which can be written as -y squared plus 4y plus 5. So that's our radius function. All right. So what we get now is that our volume is going to be pi integral from, we said c to d, right? And c to d was -1 and 5. So from -1 to 5 of our radius function squared. So -y squared plus 4y plus 5 squared dy. All right. At this point, well, we expand this. And what I'm doing here essentially, I mean, I'm not going to write the steps, but I'll tell you where this becomes expanded. I'm multiplying this by itself, right? I'm doing this, and then I'm distributing. And what that would give me is y to the fourth minus 8y cubed plus 6y squared plus 40y plus 25 dy. All right. The next thing, integrating that. Well, we have pi times this integral is y to the fifth over 5 minus the integral of 8y cubed becomes 2y to the fourth, right? Because I have to divide by 4. Plus, in here I'm going to have to divide by 3. So 6 divided by 3 is 2. In here I'm going to have to divide by 2. So 40 divided by 2 is 20. And this last part just becomes 25y. And this is evaluated from -1 to 5. All right. At that point, well, I'm not gonna actually work out all the little steps here of plugging the top and plugging the bottom, but I will let you guys do that on your own. And if you do it correctly, you're supposed to get 1296 over 5 pi. All right. And this is a volume, right? That would be the volume for that. All right. So that was doing this vertically along an axis that was not the y-axis. So now, that was the disk method. Let's talk about something called the washer method. All right. And the idea is as follows. The washer method. So the idea is this. If you had to figure out this volume, right? Let me draw this cylinder. If you had to figure out this volume, right, with that hole in there, well, how would you do it? Well, you would say that this is essentially the outer cylinder, right? So something like this. This outer cylinder minus that small cylinder, right? So the outer cylinder minus the smaller cylinder, that would give me that volume. All right. Now, in here, in terms of a washer, right? In here, this gives us essentially an outer radius and an inner radius. And that's what that's how I want you to think about this, right? A bigger radius and then an inner radius. So let's see what the washer method really becomes as far as our setup goes. So let's say that we have this. And I'm going to do this as generically as possible so you have an idea of how to apply this method in a whole bunch of situations. So let's say I had this and I had that. So here now we're taking essentially the region between two graphs, and that's what we're going to be rotating. All right. And first, I'm going to set it up here as, let's say that this is our axis of rotation. And this is the line y equals L, and we're rotating about that. Okay. I'm going to call this one up here F. I'm going to call this one over here G. All right. And we're rotating around this, so I'm just going to draw this little guy here to signify that's what our axis of rotation is. Now, to our axis of rotation and to this little guy here, we've got an outer radius and an inner radius, right? So in here, if I set up this representative rectangle, this distance is my outer radius, and this distance is my inner radius, all right? And this is going to go from let's say this is A, this is B. I'm gonna call this height here C. I'm just adding more labels so that this is as descriptive as possible. All right, so that's what we get there for this. So this distance over here is our outer radius, and this distance is our inner radius. So that tells me then that our big radius is, and I want everything here to be in terms of x. So our big radius is f of x minus L, right? That big radius is the upper bound minus the bottom, big number minus bottom minus small number. And then our inner radius, or small radius, is going to be this distance. So it's going to be g of x minus L. All right. And now let's take the idea up here, right? Like this idea. We need to take the volume of the big piece minus the volume of the small piece. So, or the volume of the bigger radius things minus the volume of the smaller radius things. Okay. So in here, what this gives us now is going to be, well, the volume is going to be pi times the integral from a to b of big radius squared minus little radius squared dx, right? And again, what I'm doing there is I'm finding the outermore one and then the innermore one, right? So that's why we end up with that. Now, in here, the outer radius was f of x. So f of x minus L. So what we get here is pi times integral from a to b of f of x minus L squared minus the lower radius, the smaller radius thing, was g of x minus L, and that squared dx. All right, so that's that scenario. Now, let's talk about the scenario slightly differently. So I'm going to copy this graph. So now I'm going to change my axis of rotation, and let's see how that changes. We're still going to figure out what the outer radius is, the upper radius, and the smaller radius. But let's say now that my axis of rotation was over here. So this is the line y equals L. Well, in here, this is still the representative rectangle. And now we've got this piece being the outer radius, the big radius, and then this piece being the small radius. So r of x, right, the radius is going to be big number minus bottom number. So big number here is L, minus bottom number here is g of x. And over here, big number is L, minus small number here is f of x. All right. And now we need to do the same exact idea. Volume is pi integral from a to b of big radius of x squared minus little radius of x squared dx, meaning that this formula is actually pi times the integral from a to b of L minus g of x squared minus L minus f of x squared dx. All right, and that's just with the axis of rotation being up here. All right, and if I talk about the little guy there, he would be up here, right, where the big radius to him is that distance, the higher distance, and this is the little distance, right? All right, so that's that one. Now let's do two more scenarios. Well, perhaps I'll just do them in the same graph this time. All right, now let's say that now we're no longer rotating in a vertical manner. This is me over a horizontal axis. We're going to rotate over a vertical axis now. So let's say, actually, can I shift this a little bit? I could. Nice. So first, I'm gonna do, let's say that we're rotating about this line right here. And here, this is x equals L. So here, all right, my representative rectangle is this now. All right, that's my representative rectangle. So when I go ahead and rotate this about this axis, well, big radius, little radius. All right. So because of that, I mean, I won't draw all the things here, but I'm going to say this becomes the volume is pi integral from c to d of, well, this big radius is going to be g minus L. So I'm going to write it as g of y minus L quantity squared minus f of y minus L quantity squared dy. All right. And in here again, the idea is that what we're doing is just a radius with respect to y squared minus a radius with respect to y squared, and big radius over little radius. All right. And that same idea can be applied if I'm rotating again about this line over here, right? If this is x equals L, and I'm rotating this way, and I've got again now my little dudes over here. So I've got this being the big radius and this being the small radius, right? So it's going to be this minus that, this minus that. So what I end up with here is that the volume is going to be pi times the integral from c to d of L minus the big radius first is f of x, right? This distance. And I should be saying f of y, sorry. F of y squared minus L minus g of y squared dy. All right. So there you go. Maybe if I draw these something like this. That's big R. That's little r for the yellow. And then for the blue, that's big R. That's little r. All right. But again, the idea is it all stays the same over here. All right. There's no real difference. All right. So let's do a couple of examples. I believe I'm at letter F, right? So that's one E. Oh man, yeah, there it is. E. Good. Letter F. Example F. All right. So find the volume. Well, I'm just gonna give you the region. So bounded by. So the region bounded by y equals the square root of x, y equals x squared. Now we're rotating, so rotate it about, let's do the x-axis. All right. So let's see what we have here. We have the function square root of x. We've got the function y equals x squared. This is x squared. Y equals x squared, and this is y equals radical x. So this is the region that we're rotating, and we're rotating this about the x-axis, right? All right, well, we already know how to deal with this, right? Because I'm going to start by making my representative rectangle. My representative rectangle here should always be perpendicular to my axis of rotation for the disk or the washer method, all right? So, well, what are we going to do here? Well, first, we should figure out what these bounds are. And how do I figure out what these points are? Well, set these two functions equal to each other to see where they would be the same. To get rid of this radical, square both sides. So I have x to the fourth is equal to just x. Move the x over. X to the fourth minus x equals 0. Factor in x. Solve for x. So we have 0 and 1. Okay, 0, 1. Cool. Now, the next thing we're going to do here is say, well, what should our setup be, right? And, well, we're going to say the volume is going to be pi times the integral from a to b of big radius minus little radius, and each of these pieces squared. So what does that give us? A to b. We just said that the bounds were 0 and 1. Big radius. The big radius here is going to be this distance, right? So if my little guy is here, this is the big distance. That's the big radius. And then this right here would be the little radius. So this is big R, this is little r. All right, so big R, it hits up to square root of x. So what we have here is square root of x squared minus little r. It hits up to, what was that, x squared? Y equals x squared? Yes, it is. So we have x squared squared dx. So now I have pi times the integral from 0 to 1 of applying these. I end up with x minus x to the fourth dx, right? And taking the integral, I end up with pi times the integral of x is x squared over 2 minus x to the fifth over 5, evaluated from 0 to 1. Plug in the 1, so I have 1 squared, so it's 1 over 2, minus 1 to the fifth, that's just 1, and we have that over 5, minus pi times 0 minus 0. In other words, that part is irrelevant. And then 1/2 minus 1/5. Well, the common denominator there is 10, right? And this one becomes 10 minus, not 10, 5. 5 times 1 is 5, minus 2, which gives me 3 pi over 10. All right. Next one. Let's complicate this a bit. All right. And here we go. So G. Let's say that my region is y equals x squared, y equals x. All right, so bounded by those two, and we rotate it about x equals 1. So let's see what these look like. So I've got x squared, which looks something like this. We've got y equals x, which looks something like this. And we're rotating about the line x equals 1. Well, before I put that here, let's see where these two are equal to each other. X squared equals 2x. Move the x over. X squared minus x equals 0. Factor in x. X times x minus 1 equals 0, which means that either x equals 0 or x equals 1. So they actually meet, in fact, at 1, which is what we're rotating about, right? Let me just draw this a little bit better. So something like that. And here is my axis of rotation. All right. But this is the region that we're rotating. And in here, well, let's get our little guy here. To him, well, what is the top function? It's this. What is the bottom function? It's this, right? And in fact, in here, if I look at my representative rectangle, that would help, right? And now we have the big radius and the little radius. Now the big radius, what is that big radius going to be? Well, this line we just said was x equals 1. So the big radius, and we need this to be in terms of y. Why do we need this to be in terms of y? Because, well, we're doing a vertical, a rotation about a vertical axis. So that means I need things to be in terms of y. So from here, since y equals x squared, I can say that x equals the square root of y. Since y equals x, I could say that x equals y. All right, this wasn't that exciting. But in here, we found our function as of y, right? So this big radius is going to be this line minus this line, right? So this value minus this value. So that's 1 minus this line, which is x. Little radius in terms of y. Hold on, not x, y, right? Because I need this in terms of y. So 1 minus y. Little radius. So I have 1 minus this curve. And this curve was radical y. So now that I've got my outer radius and my inner radius, I can figure out the volume. And we can say now that the volume, well, it's pi integral from c to d of r of y squared minus r of y squared. But obviously we mean big R and little r. And now, well, let's see what we get here. Plug in these values in here. Well, we already did the hard part. C to D. We need those to be in terms of y. This value right here is 0, but this value up here, what is that? Well, plug in 1 into either of the two functions. I get 1, right? So that point is 1, 1. So there, that value there is 1. So we're going from 0, from this 0 to that 1. All right. And to go from 0 to 1 of our big radius, 1 minus y squared, minus our little radius, 1 minus radical y squared dy. All right. And I mean, we already did the hard part. The hard part is the setup. All right. I will let you guys finish this one on your own. All right. I highly do encourage you to finish this integral. All right. All we need to do is FOIL this, FOIL that, integrate, all right, and evaluate. But this should give you pi over 6. All right. So if you don't get pi over 6, you probably messed up somewhere. So I'm letting you practice this integral on your own. Now I want to look at a slightly more complicated version of this one. All right. Let's say that I had the following. So that was example G, right? G. So H. Let's say I have f of x is equal to 4x minus x squared, and g of x is equal to x squared minus 4. And then we're going to say, so we want the region bounded by that, rotated about, let's say y equals -8. All right. So I'll help you do this. So here again, I'll do the setup so you can see what to do. So let's see what we do here. 4x minus x squared and x squared minus 4. All right. So those two were carefully chosen. 4x minus x squared, that's a parabola facing downwards. And it looks something like this. All right. The other one, x squared minus 4x. I missed the next. X squared minus 4x. It looks like this. So perhaps I should have done this in two different colors. So let's redraw this first one in yellow, and again it looks something like this. Right. And then the other one we'll do in blue. And it looks something like this. Yeah, they're meeting here at the same spot. Perhaps I can shift that. Oh, look at that. Close enough. All right. Now, these points of intersection, I mean, how would I figure out what they are, right? Well, I would set these two equal to each other, but I mean, I could tell you right now that it's just the x-intercepts, and either way, whether I look at, well, let me look at g of x. So if I find the x-intercepts, that's where y is equal to 0, right? So I set the function equal to 0. So I have x times x minus 4 equals 0. So x equals 0, x equals 4. All right, so 0 and 4. Okay. But we're rotating this about the line y equals negative 8. So what we're doing here is, let's say that this is negative 8. We're rotating in it about that line, y equals negative 8. So in here, my the little guy is going to be right here, right? And my representative rectangle, well, it will look something like this. That's my representative rectangle, where this distance over here, that would be my big radius, right? In terms of x, because we're rotating about a horizontal axis, and this would be my little radius in terms of x. So what does that mean? Well, r of x, the big radius of x, this distance up here, well, that's the yellow function, which was 4x minus x squared. So we have 4x minus x squared minus negative 8. And then the little function r of x is going to be x squared, right? X squared minus 4x minus negative 8. And they're all both going to be going from 0 to 4. So our setup now, it becomes the volume, so pi integral from from a to b of big radius squared minus little radius squared dx. So what does that really give us? So we're going to say this is pi times the integral from 0 to 4 of this thing right here. I'm going to write it as 8 minus, 8 plus 4x minus x squared, squared again, minus the little r. So I'm going to write that now as x squared minus 4x, but now we've got plus 8. And then this is also squared dx. All right? So that's the setup right there. At that point, well, I'm going to let you guys finish this up. What do we need to do? Expand this, right? We're squaring this, so we have to make sure that we think about it this way and multiply them. Similarly with this one over here, put them as two parentheses next to each other and distribute. So when we evaluate whatever that gives us from 0 to 4, we end up with the following: 1024 over 3 pi. All right, so I encourage you, in fact, you should really be finishing this integral on your own to see that you get that answer. I'm gonna do one last example here, and this is example I, and it says, well, it's gonna be bounded by the following. Let's say we have a region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1, rotated about the y-axis. All right. So let's see what we get here. X squared plus 1. So let's see. Let's look at the region. X squared plus 1 looks like this. It is a parabola shifted up by 1 unit. y equals 0, well, that's just the x-axis. X equals 0, that's just the y-axis. X equals 1, that would be this right here. All right, x equals 1. This is 0. So this is the region that we're rotating about the y-axis. All right, this region, this entire region. All right, now let's see what the issue is here really. What we have here is that in this piece up here, we've got this representative rectangle, but in this piece down here, we've got this representative rectangle. And that is an issue because, well, they have different, while they're both are going to have the same big radius there, they're going to have different small radiuses because this bottom one doesn't even have a small radius. So what we really need to do here is set this up as two different integrals and add it all up together. All right. So this first integral here, I'm going to call that volume 1. This is going to be volume 2. And the entire volume is going to be volume 1 plus volume 2. All right. So the total volume. And just to get an idea as to what this might look like when we rotate that region, let's see. Let me erase some things here. So it'll look something like this. And perhaps I should do this one dotted as well. All right, there we go. So that's essentially what that will look like. All right. All right. With this gap inside here, right? Now let's see how to set this up as our volume. So we say volume 1 plus volume 2. Well, volume 1, what is that going to be? Well, volume 1 is going to be using these two radiuses, right? Where we've got there this being the big radius and this being the little radius. So we've got pi integral from, we need y values for our bounds. We know that this value is 1. This value though, well, let's figure out what this point is. When I plug in 1 into our function recall was x squared plus 1. So when I plug in 1, I end up with 2, telling me that this height is at 2. Okay, so volume 1, the integral from 1 to 2 of our outer function, that's going to be the big value minus the small value. So that's going to be 1 minus this function. Well, we need that to be in terms of y, right? And from here, since we know that y is equal to x squared plus 1, well, then x is going to be the square root of y minus 1. All right, subtract 1 over, take the square root of both sides. So that is just that, the outer radius. Excuse me, the outer radius is just 1 minus 0, sorry. And then that's squared. Sorry, I was getting ahead of myself talking about the smaller radius. But the outer radius is this distance minus this, right? So that's 1 minus 0. All right. Now, the smaller radius, that's this minus this. This point right here minus this point right here. Well, that one's the function, but it needs to be in terms of y, which is fine because we're still in here this piece. So minus the square root of y minus 1, and then technically minus 0 because that is a small value here, right? Okay, and then that squared dy, which, I mean, this is really just saying the integral So this is volume 1. The integral, well, pi times the integral from 1 to 2 of 1 squared, which is 1, minus the square root of y squared, which is just y minus 1 dy. So that gives me pi times the integral from 1 to 2 of 1 minus negative 1. That's 2. Minus y dy, right? And in here, what does that give me? This gives me pi times the integral of 2 is 2y. The integral of negative y is negative y squared over 2, evaluated from 1 to 2, giving me pi times, plug in 2. 2 times 2 is 4. 2 times 2 is 4, divided by 2 is 2, minus, plug in the bottom. 2 times 1 is 2, minus 1 squared is 1, divided by 1 by 2, excuse me, is 1/2. So 4 minus 2 is 2, so 2 pi minus 2 minus 1/2. 2 is 4/2. 4/2 minus 1/2 is 3/2. So we have 3/2 pi. And then again here, 2 minus 3/2, well, 2 is 4/2. 4/2 minus 3/2 is 1/2. So here I end up with just pi over 2. But that's just volume 1, right? Pi over 2. Volume 1 is pi over 2. We got to figure out volume 2 to figure out the total volume. So volume 2 is this region down here. Okay. So let's look at that. I'm going to erase that from there. That bottom volume, volume 2 is going to be pi integral from a to b. We're in here, we're going from 0 to 1 of just 1, right? That's my outer radius. That's my only radius. So it's just 1 squared dy, which gives me pi times the integral of 1 is just y, evaluated from 0 to 1. Plug in the top number, so I end up with pi minus, so pi times 1 minus 0 times pi, which is just pi. And at that point, we're going to say, well, we know that our total volume was volume 1 plus volume 2, which is just pi over 2 plus pi, which is 3 pi over 2. All right. Now, the point of this problem, again, was to show that, well, there's not always just given the region, it's not just always just one setup, right? I ended up having to do 2 different volumes being added up, right? And we again need to keep in mind that this radius, the big radius, is this value minus this value, right? From there to there. And the little radius is just from here to there. But because we're rotating around a vertical axis, everything needs to be in terms of y, all right? So all of these needed to be in terms of y, which is the reason as to why we needed to change this function to be in terms of y. Okay, that concludes the end of 7.2. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.